thermoplastic composites are expensive because of the cost of matched tooling, which is why it's mostly used in high volume applications. What if you could throw away half of that tooling? In this video, I'm going to be going into the reasons why thermoplastic composites are so expensive and the disrupting technologies that are addressing these issues. And I'm going to be expanding on what these technologies are, how do they work, and the use cases. So let's get into it. Hey, what up? This is Yatin and welcome back to ThermoForge. A couple of months ago, I was at JC Paris and I came across a company that was talking about technology which was very promising, but to my shock, they actually have this technology in production that companies can just go and use it to really reduce cost for thermoplastics. So when it comes to thermoplastic composites, one of the main challenges that we have is if you compare it maybe to thermoset. With thermosets, because the resins are low viscosity, you can actually impregnate quite easily your material, but with thermoplastic composites, you need to apply a lot of pressure because the viscosities are quite high, and you also need to apply fairly high temperatures too, which can be a bit of a challenge. I'm going to be showing you a video from Angle to kind of like demonstrate where these costs are. There is a stack of thermoplastic sheets and you have a bunch of grippers that picks it up, and you can already tell the amount of automation that is required to work with this material. So the thermoplastic sheet has to be heated past its melting point. In this case, it keeps on going up to around close to 400 degrees, so probably a peak material. So very high temperatures, which takes some time. And once it's past melting point, that sheet is formable and pliable. It gets picked up and then placed into an injection molding tool. Sheet is placed, pushed into the injection molding tool, and is going to hold it in there and overmold around it. So the first big contributor of cost is you have seen the tooling. The level of complexity on the male and female tool is very high to make this part. And what this means is if you want to do some prototype and you want a quick turnaround, it's not going to happen. The manufacturing time for making the male and female tool is very long. It's usually 3 months plus. And if you want to prototype, the costs are incredibly high. And also, if you want to bring down your unit cost, you need to make these parts really fast. And there's a thermal cycle that has to happen there where the temperature has to go up. You have to injection mold the polymer in there, and then you have to cool it down, and all that temperature change just takes a lot of time. The speed needs to be really fast to be able to save some cost on this. This now brings us onto one of the disruptors that I came across. So I was at JC Paris and I came across Roctool, who make induction heating tooling. I'm going to go explain what induction heating is very shortly. And what Roctool did was they addressed this problem in two prongs. One is the thermal cycling to happen really fast for an induction system, and the second one is the tooling cost. Rather than have a male and female tool, they only have a male tool, and then they use a silicone system on top to conform around the tool. Let's hear directly from Roctool.
Like our ambition is just to demonstrate that induction can be used in many different configurations, from a bed plate on a press machine to a light tooling solution with a silicone membrane to avoid having a big machine. So induction heating can do so much and can replace all the heating systems such as oil or hot water.
So let me pause on induction heating. So most conventional systems, when it comes to compression, injection molding system, they use a resistive thermal rod. So it's just a rod that is inserted into the tool, and that rod will heat up and transfer heating into the tool. So these are fairly conventional and straightforward systems. But what induction does is different. Induction is going to transfer that heat through an electromagnetic field and that EM field is going to heat exactly the part that you need in the tool. So a standard heating rod system will just heat up the whole tool, and then it takes a long time. Whereas with an induction system, you can dump in a lot of energy exactly on the surface that you need, as in the tooling surface, rather than heating the whole tool. So now you can see the video from Roctool, where at the bottom you have a structure, and placed upon that structure is actually the mill tool. So the mill tool is placed in there, and coming on top of the mill tool, you will see what is the silicone system at the top. So let's do a bit of a breakdown. On the mill tool, you can see there's some induction heating system in there, which will heat the tool specifically. And at the top, you have a silicone type membrane, and this membrane will conform around the bottom tool. And as you can tell, some sheets have been placed here. In this case, some pre-preg type thermoplastic or even thermoset. You can apply a vacuum in there, so the vacuum will apply 1 bar pressure onto the parts while you get the temperature up. But what's possible about this is you can also apply positive pressure, which what Roctool is doing here. We're applying positive pressure to 10 bar, which is more than plenty when it comes to thermoplastic composites. We ramp up the temperature to around, in this case, 240, which is to get the material past melting point so that it can fuse. Now you can do an accelerated cooling. As you can see, the temperature is dropping down. So the cooling now will simply fuse the material together and leave it in the shape that it was originally on. But everything that is happening right now is happening within minutes. So in something along the lines of 3 minutes, you can have actually a part. If you were to make that exact same part in an autoclave, the time for that would be incredible. You're talking easily 4 or 5 hours on the lower end, whereas in this case you made that part in 3 minutes. Time is money, and that's what Roctool is demonstrating here. Let's get back with Roctool.
So if you do have the silicone bladder, today silicone in an industrial way can go up to 250 Cs.
Wow.
Okay, so that actually drives what you can do in terms of material, which would include some of the nylons, some of the polypropylene.
So you get lower temperature nylon, nylon 11, nylon 12?
Some of the lower nylon and polypropylene, but we also do
100%.
some of the sometimes other thermoplastic resins like PLA. So I think down the road we see an evolution on the silicone bladder. We have some developments with partners that are working on high heat silicone solutions that potentially will go to 300, 350.
Oh wow,
which
350.
Then,
so you're looking at PPS, maybe close to peak.
So then we could potentially unlock some of the more higher heat. So right now we don't have yet that silicone, but as soon as we have it for sure, we will demonstrate it.
And then earlier I heard you talking about the opportunities with silicone. So when you have two metallic tools, you need like a draft angle so that you can release. But with silicone, you can actually drape around the tool, right?
We have more possibilities with silicone. It's not magic, but it does open up more of a contour and also some of creating an iso thickness, because silicone is definitely your best friend when you're molding, because it will guarantee an even pressure.
The force, rather than going in this direction, with silicone you can have force going in this direction.
You can have force because we also pull vacuum plus the silicone, so this combination makes a very even thickness. For the show this year, we're showing different thermoplastic solutions, and especially different reinforcements. Some are flax and some are carbon fiber. The flax is coming from Ecotechnila this year, which is one of the largest. And for the non-woven material, those are recycled carbon fiber from Yuho. Coming from Japan. They have a unique non-woven material where we get such a good surface quality with the induction.
That looks really good,
because we can drive the resin and we can show how the resin create like a resin-rich surface.
Yeah, definitely. And what resin do you have on the recycled fiber in there?
That's PP. And exactly. For the demonstration here, we decided to do a lower cost resin because we wanted to show that composite and you can get some level of performance with a lower cost resin with amazing reinforcements.
And especially with the recycled fiber, it's more accessible. So you want more accessible resin systems within them. Awesome. Well, every time I come back, every time I'm excited. It's an absolute
Thank you
pleasure
very much for
to always speak
the
to
opportunity.
you. Yeah, thank you very much. Cheers.
As you can tell, thermoplastic composite doesn't need to be locked behind the restriction of very expensive tooling, where you have these emerging technologies which are actually enabling a lot of companies to be able to do prototyping and all that sort of stuff. In future videos, I will be going a lot deeper in these technologies such as induction and so on. But in the meantime, if you enjoyed what you've seen, click the subscribe button. There's a lot more coming, and I will see you then. Peace.